Hello, everybody. Thank you for joining us today. My name is Ronaldo Pinto. I'm the Technical Sales Director for Applied Field Technology. My email is ronaldopinto@aft.com. And I'll be conducting today's webinar that we have titled Modeling a Ramp Pump. If you have any questions during the presentation, feel free to type it in the GoToMeeting chat room, and at the end we'll have a session of questions and answer. Well, I'll try to answer all the questions, and if we don't have enough time, you'll receive an email with an answer to your questions. So a brief description of what we're going to cover today. We're going to be talking about what a ramp pump is, history of the ramp pump, a brief history. How does a ramp pump work? Modeling a ramp pump and AFT Impulse, disadvantages of a ramp pump, why use a ramp pump, conclusions, and then a session of questions and answers. So what is a ramp pump? Interesting story. I learned about a ramp pump talking with a Uber driver that was taking me to the airport. And I always like to talk with the Uber drivers because they always have something interesting to say. And this was a technician, and he told me that he designed ramp pumps and installed them. So I asked him what a ramp pump is, and he mentioned that a ramp pump is a pump that builds pressure using water hammer. I found the topic interesting. I came back to the office, did some research, and prepared this presentation that I'm sharing with you today. If any of you have real experience with ramp pump and wants to share with us, feel free to send me an email and I'll share it with all the attendees. So a ramp pump, or hydrant, as it's also called, is a cyclic water pump powered by hydropower. It functions as a hydraulic transformer that takes the water at a hydraulic head and flow rate and outputs it at a higher hydraulic head and lower flow rate. The device, as I mentioned before, utilizes water hammer effect to develop pressure, and this is what caught my attention. So a little bit of history of the hydraulic ramp pump. To my surprise, the ramp pump is a mature technology. Before invention of petrol engines or the arrival of electricity on farms, the ramp pump was used in many locations, being the only feasible way of lifting water from streams or springs to neighboring hillsides. The first hydraulic pump was designed by a British man called John Whitehurst in 1772. He installed the first set of hydraulic ramp pumps with the caveat that they could not operate automatically. Its valve had to be shut manually to create the force of water hammering for water lifting. And being a cyclic pump, this is a limitation for the pump. The automatic ramp pump was invented by a Frenchman named Joseph Montgolfier in 1796. So how does the ramp pump work? So let's talk about the components before I describe the operation. We have a water supply that we'll see that it's basically a infinite source of water, like a lake, stream of water, waterfall, a river. It has a dry pipe that allows the water to flow to the ramp pump. It has a waste valve, which is basically a check valve. It has a delivery valve, which is another check valve. And the two last ones, the waste valve and the delivery valve, are the only moving parts of the ramp pump. It has an air chamber. It has a delivery pipe, and it has an intake tank, which is the community we want to deliver the water to. So the basic idea behind the ramp pump is quite simple. The waste valve allows the water to flow initially through the dry pipe and builds up speed. Once the water reaches its maximum speed, the waste valve slams shut. Due to the water hammer effect, the water, due to the inertia, wants to continue moving past the waste valve. And due to the water hammer effect, the pressure inside the ram pump will rapidly increase enough to force the delivery valve open. This forces some water into the air chamber, compressing the air chamber air. The pressurized air forces the water through the delivery pipe to the intake tank. The pressure in the pump falls, the waste valve reopens to allow water to flow and build up momentum again. The delivery valve closes and the cyclic repeats. So let's see graphically what I've just described. The waste valve allows water to flow through the dry pipe and build speed. So initially the waste valve is open, and this is achieved in the installation by putting the check valve in vertical position, so the weight of the disc will allow the initial flow, and then when the water speeds up, it slams it shut. And once the water reaches the maximum speed, it slams shut, and the pressure inside the ram pump will rapidly increase to force the delivery valve open. This is due to the water hammer. So the water flows down to the ram pump, the waste valve closes, it opens the delivery valve, and the delivery valve, this forces some water into the air chamber, compressing the air in the air chamber. The pressurized air forces the water through the delivery pipe to the intake tank, and this is how it operates. So let's see a video of how it works. So we see that water initially flowing through the waste valve to the waste valve slams shut, builds the pressure inside the ram pump, the delivery valve opens, compresses the air in the air chamber, and this delivers water through the delivery pipe, and it closes the delivery pipe. The pressure in the ram pump goes down, it opens the waste valve again, the water flows to the delivery pipe, builds up inertia again, it opens the delivery valve, compresses the air through and the cyclic continues. So this is how it operates. It's quite simple. As you see, no energy, no electricity is required. So let's build a model in AFT Impulse. What we're going to try to model is, the problem that we're going to try to model is the water needs to be pumped to a remote community with limited access to energy sources. The water supply is river, hydraulic head available is 8 meters, and the community elevation is at 50 meters. So AFT, the water supply as we see here is at 8 meters, that we'll see that in the model. The community elevation is 50 meters. And I used the bypass to simulate the initial flow through the waste valve that builds momentum into. So what do we see? The water supply initially flows and it goes through the bypass. Then the bypass closes due to water hammer effect. The pressure builds in the ram pump, opens the delivery valve, compresses the air in the air chamber, and this forces the water through the delivery pipe to the intake tank or the community we want to deliver the water to. Our initial guess would be a pipe size of 2 inches. So I'm going to bring the impulse model. Let's see the transient for the initial flow. We can see that I closed it in 0.1 second. So initially, the water flows through the delivery pipe, through the bypass, and then it slams shut, and it's going to build pressure here. So what we're going to see is the waste valve and the delivery valve, which are check valves, closing and opening, and the delivery pipe, the water flowing, the air in the air chamber being compressed, and it's going through batches to the delivery pipe. So we run it, it's already run. We're going to see the output. And we're going to take a look at the event messages to see if the ram pump is operating. So we go to the event message and we see the check valves closing and opening, which means that the ram pump is operating. So now let's look at the graph results. We're going to see the delivery pipe. So the delivery pipe, we see the batches of the pressure going up and down due to the pressure static due to the water hammer effect. Let's see the volumetric flow in the air chamber. So we see the liquid volume going up and down. Initially, we see a big spike due to the initial water hammer, and then we see the air in the air chamber compressing more, less drastic than the initial one. And let's see the delivery pipe. So the volumetric flow, we see that it goes up by batches. And the integrated volumetric flow, we see that it increases in time up to 6 cubic meters in 10 seconds. So let's see the visual report, the visual results, and see how it operates. So I'm going to graph the volumetric flow. So what we'll see in here is the water flowing from the delivery pipe through the bypass. And when it closes, then we see the pressure cycling and the check valves closing and opening and allowing the water to flow to the air chamber and flowing through the delivery pipe to the intake tank. So I'm going to run them, play the video. So initially we see the red one flowing through the bypass. Now the bypass closes and this pressure starts building. It opens the delivery valve and water starts flowing down the delivery pipe to the intake tank. And it continues, and then it opens less drastically, but it continues to flow and it operates automatically. So now we're going to see, we're going to compare if we use 3 inches. So I'm going to use a feature I created 3 scenarios. 1 for 2 inch, 1 for 4 inch, 1 for 3 inch. I'm going to run it to compare them graphically. And I'm going to use a feature here, an impulse. I'm going to do a batch run because I don't want to run one by one. I'm going to look at the scenarios. Okay, I want to see the 2 inch, 4 inch, and 3 inch. Say okay. I say, okay, start run. So it runs the first scenario. Runs the second scenario. runs the third scenario. And why do we run it? Because if we want to compare scenarios rapidly, we have to have the output for all the scenarios we want to compare. So now we go to the graph results. And what do I want to see? I want to see the delivery pipe, the outlet. We want to see the integrated downstream. We say generate. And here's the scenario for 2-inch. I want to compare it. So to compare scenarios, I'm going to use a new feature in Impulse, multi-scenarios. I want to select the scenarios I want to compare. I want to say, okay, I want to see 4-inch and 3-inch. Say, okay, generate. And now we see that although initially the 4-inch pipe delivers more water, the same as the 3-inch, it fades away in time, and while the 2-inch continues to grow. So most probably bigger diameter pipe is not good for a ram pump, and 2-inch pump is an ideal size for the ram pump because it doesn't fade down in time. Another thing I would like to see is the in chamber. And as I mentioned before, due to the water hammer effect, it compresses the air cyclically, and it delivers the increase of pressure in the air chamber is what forces the water through the delivery pipe, because the waves on the delivery pipe doesn't allow the water to come back. So the water pressure builds up and forces the delivery pipe. So we saw the model, we saw the 2-inch, we saw the pump operating, basically increasing the pressure using water hammer. But what are the disadvantages of a ram pump? Big disadvantage of a ram pump is that it wastes a lot of water. Typically, only about 10% of the water it consumes actually makes it up to the delivery pipe, only 10%. So that's why when I mentioned the source of water, I mentioned a river, a lake, a waterfall. The rest of the water flows out of the pump, and the water builds momentum. So why do you use a ram pump if it's so inefficient in the volume of water it delivers? Well, basically, they need no external source of power. The force of moving water gives them the power they need. They are extremely simple with just 2 moving parts. This pump can be easily used everywhere, even if there's no electricity or other resources such as diesel. And as a matter of fact, we're working on a project with a nonprofit organization in El Salvador that is designing a ram pump to deliver water to a village in Salvador. So we might not see the ram pumps at great scale, but it's still used in some place where there's no electricity or other source of energy. So conclusions. Ram pump can be used as an example to show how severe a water hammer can be. For example, in the pump, if the pump is 10 feet below the pond, the delivery pipe might be up to 100 feet up the pump, only using water hammer as a source of to increase the pressure. So imagine it can increase 10 times your pressure. Imagine if you have a system where water hammer is happening, the forces you can get due to water hammer effect in your system. So it's water hammer or surge pressure is always something you have to be careful about. And ram pump is a example of how critical water hammer can be. Another conclusion that we drive is ram pump is a good option for remote areas. As I mentioned, we might not see it in great scale, but it's still useful. And for remote areas where there is both a source of low head hydropower and a need for pumping water to a destination higher in elevation than the source. In this situation, the ram pump is often useful since it requires no outside source of power other than the kinetic energy for the water. So, is there any questions? So there's a question here. Let's see, share here. Sorry you couldn't hear me. Let's see, I'm going to look for the question. I always have problem with the. Let's see. I cannot see the questions. Let me see. Any book recommending the water ram pump? As I said, I've heard about it the first time and I did this research. So I really don't have any recommendations of a textbook for it. What about 2 or 3 waste valves? Yes, I don't have no practical experience. I just found the topic interesting to bring it up. The way to make it more efficient is a topic that I would like to do some research on. But so using 2 or 3 waste valves might be a way to improve the efficiency. I'm not sure about it. Okay, so let's see. I'll look at the questions. I can't find more questions, but thank you for joining us today. This is a topic that I found interesting and I want to share with you. if you want to continue the discussion or want to receive the model that I created, it would be more a pleasure than send it to you. And regarding how to make the ramp pump more efficient, that's another thing I would likely share with you and work at the model and see how we can improve the model. But it's something interesting. I never had heard of a ramp pump, and this is my first contact. So thank you for joining us today. You're welcome to join us in future webinars, and I hope you found the topic interesting, and see you again next time.